Good afternoon and welcome back to the Nexperia Power Live Packages channel. We continue our live discussions now with MOSFETs for use in high continuous current applications. So this particular session is scheduled for approximately 25 minutes. As with all the other sessions that we've done, we'll present a 10-minute presentation and then open the floor for your questions. So please do send your questions in. You can use the chat function at the bottom of your screen, and all questions are anonymous as well, so feel free to ask any questions to our experts. We're joined by Stephen Waterhouse, Product Manager, and Sami Ahmed has stayed around. He's Senior Applications Manager, both from our MOSFETs division here in the UK. And with that, I'll hand over to Sami to begin.
Good afternoon, and thank you for joining us. Stephen will start the first couple of slides, so I'll pass on to Stephen.
Okay, so thanks for joining. Yes, today I want to talk about high current applications and MOSFETs for use in high current applications. And this is high continuous current. We talk about the high continuous current both in normal and expected fault conditions. Okay, so what do we mean by high continuous current? You can see from some of our data sheets in the headline, we put some quite high numbers in there. So if you have a look there, we've got the PSMR 5125 YLH, and this is a 380 amp rated MOSFET. And when we talk about that 380 amp rating, this is a DC current. So it's not a pulse current. It's not something we expect you to pulse for 10 milliseconds. This is a DC current. And this is based on us having a fully enhanced MOSFET. So you can see there in the conditions that the VGS is 10 volts. And it's also based on the mounting base being 25 degrees C. Okay, so this isn't really what you would see in most circuits, but we need a baseline in order to see the capability of a MOSFET. So this is your DC current rating, not IDM. I'm going to pass over to my colleague, Sami, who's going to talk about a couple of applications that need this high current rating and how we actually achieve it with our MOSFETs.
Thank you, Stephen. We have listed some of the applications here. By no means this is the full list, but pretty much similar configuration of MOSFET are shown here where high current is necessary. For the motor drive, we have now terms in kilowatts, power in kilowatt terms is a commonplace now for a motor drive, and therefore high current is of relevance. For O-ring or load switches, another two applications where high current is necessary. Perhaps one of the most obvious place where a MOSFET is required to handle high current is the battery protection, where pretty much all the current of the system is made to go through that MOSFET. Another one where we will focus slightly on is this battery protection, where not only it has the high current MOSFET capable, but it also has a fuse for an extra safety mechanism. Now, to just put things in perspective, you see the fuse reaction where it would take a few tens, if not 100 milliseconds before it shuts off or provides that protection. Now for the MOSFET, that is already in DC condition, as will be explained in a moment. So looking at the thermal impedance of the MOSFET, we have what we call a transient region for pulses up to about 100 milliseconds. But from about 10 milliseconds onwards, you see the response starting to plateau, and it flattens anything above 100 milliseconds. What does that mean? It means that the MOSFET, as far as the MOSFET is concerned, any current lasting 100 milliseconds onwards is already making the MOSFET operating in a DC state or steady state region, and therefore continuous is of relevance. What we do at Nexperia, as mentioned by Stephen, is that we do actually the testing. Now, It is perhaps sufficient to test to 1 millisecond, because that would be a genuine steady state. At Nexperia, we test above 30 seconds. So the current rating that we have are tested and verified in the lab. What allows us to have this high current capability is the actual package, amongst other things, such as the die and the structure of the silicon. Now, the silicon itself is sandwiched between two copper plates, the drain tab as well as the source tab, or the source clip bond. The advantage that the source clip and the drain tab being two pieces of copper where the silicon is sandwiched in between, it gives it this nice uniform current share or current spread. It achieves low RDS on. It reduces the parasitics, especially inductances. It provides a very low thermal resistance, which is a direct contributor to achieving high currents. Now, the source clip, as well as providing the uniform spread of current, it also provides a channel for thermal path to dissipate this high power. So the LFPAK itself, the way it is structured, it is a perfect fit for high current application or high current capability. Its manufacturing is done in few steps and provides it with a robust and reliability that the LFPAK is known for. If we were to compare an LFPAK against the wire bond MOSFET, in this case, we have an LFPAK 88 against the bigger package, the D2 pack. We see here that the wire bond, the surface being a small, the surface of the wire bond connected to the die is smaller, therefore the concentration of current is higher. So it has a current crowding issues that the LFPAK, because of its, or thanks to its source clip, avoids this current crowding. Another advantage that LFPAK has against the wire bond. And with that, I hand over back to Stephen.
Okay, thanks, Sammy. So it's clear from the last previous couple of slides that we rely on that full copper clip LFPAK technology that allows us to deliver this maximum current. Let me go back to previous slide. So we talk about maximum current, but this is a current that we're happy to put on our data sheets. When we are in the lab, we usually test to a much higher current as well. So we know that the MOSFET itself is capable of a higher current. We don't take it up to its 175 degree max rating. But again, that just stands out that the full copper clip LFPAK technology gives us that capability. Because a lot of circuits and applications require a high pulse rating as well as a DC current, that pulse rating is derived from your DC current. So normally it's 4 times the rating. So that's required for your transient event. So if it was a startup or a fault condition, so if it was a locked rotor or trying to get a golf buggy to mount a curb or something, that's where you need that high pulse current rating. We know that the LFPAK is best in class in terms of power and current density. In fact, we have a device which is an 8x8, and you can see there at the bottom that delivers up to 48 times the power density when we compare to a D2 pack. And not only that, because we've got this full copper clip construction and there's no internal wires or glue, we know we get a very low electrical resistance, a very good low thermal resistance, and also the inductance is very low as well. Next slide, please. Okay, so I've detailed a few Nexperia products here. I focus on the R5125YLH at the top left there. That's a 380 amp rated device. That means that if you was to pulse that device, you can get over 2000 amps for a short period of time. And that may be what you wouldn't want to do that all the time, but for a short period of time to get a motor started or a ramp up started, that's the sort of current you may require. I mentioned the LFPAK 88. So again, that's DC rating is 425 amps. and that's 2,258 amps pulse rating. You can see there's an image on the right there. We actually have a demonstrator kit, and this demonstrator kit, you can see there we've got some glowing wires on the bottom right of the kit, and that's just simulating an electrical load. So we use wires. We know that when we've got high current flowing, they're going to get hot and start to glow. And you can see from the current meter there, we've got 200 amps flowing, and the MOSFET is still about 50 degrees C. This is a DC current. It's not something, we've not done anything special. We don't press that button which sets off a chain of pulses. This is a DC current. And when we demonstrate this kit, we show that when you turn off the MOSFET, all of the inductance within those circuits and those load wires would cause the avalanche of the MOSFET. So not only can we deliver 200 amps DC in this demonstrator, we're actually avalanching that current as well. We've got an online video that shows in more detail this demonstrator in operation, and Kelly will be able to tell you where to find that on our web pages. But for now, that's the end of my presentation, and if you have any questions, we'd be happy to answer them.
Super. Thank you, Stephen. Thank you, Sammy. Okay, let's open the floor for questions. Just to remind you, all questions are anonymous. You can send questions by using the chat function at the bottom of your screen. We have a couple of questions in already, so let's make a start. Stephen, for the 380 amp, are these devices available now, and do you intend to achieve higher current in future?
Yes, the 380 amp is the R5125 YLH is part of a platform that we launched earlier this year. So yeah, that's available now. Or we can provide samples, or it's available to order via your customer service rep.
And do you intend to achieve higher current in the future?
Yes, we always test the capability. So as we develop new products which may be lower RDS on, it may be that we develop parts with a higher current rating. But be aware that the R51, the 380 amp stated, is not the actual limit of the device. That's the limit of a device that we're happy to stand with our hand on our heart and put on a data sheet and ship products. The actual capability of that product is much higher. It's just we do not have at the moment the ability to test those higher currents in a repeatable and reliable way.
Okay, thank you, Stephen. The next question is pulse current rating measured or calculated? And if calculated, then how, at what mounting base temperature?
So normally the standard for your pulse current rating, the standard, there's a de facto standard, which is 4 times the ID max. And this is normally calculated at a mounting base of 25 degrees C. However, we are developing the capability in-house where we can test this current rating. And I've seen some results of this early testing, and we can exceed that 4 times in most cases. But again, once we've got a released test method that we can prove is repeatable and reliable, that's when we'll start putting the actual measured IDM max onto data sheets. And it may be that for special cases, we can actually do some testing to find out the rating of a specific part in a particular application.
Okay, thanks, Stephen. The next question is, if I have a short circuit in my application and the current exceeds the ID, would it result in 100% failure of the MOSFET?
I can take that one, Stephen, if I may.
Yeah.
So the rating that we give, first of all, just to establish the continuous current applies to DC conditions. Now, the short circuits, all depends on the actual pulse. If the pulse is 10 milliseconds and below, then it is expected for the current to be higher to this continuous rating. And it's likely that it was vivid depending on the capability and the characteristics of the short circuit pulse. We can provide supports to do the specific analysis on that, but so it won't necessarily result in 100% failure, depending on the actual pulse itself. For DC, if the actual pulse, although we say pulse, it results in a pulse above 10 milliseconds, 100 milliseconds, then you'll be looking at the current rating that we give. And for that, it is advised to stay within those limits or below.
Okay, thank you, Sammy. The next question is there a time limit to handling a high current?
I can also answer that one, Stephen. So basically, the limits that we give in here are DC, meaning it's continuous. But the conditions have to be fulfilled. One condition is that the mountain base temperature needs to be maintained at 25 degrees for these particular figures that we give in here. What this means is that if that temperature is maintained at the mountain base, the drain tab, then yes, you can apply that current. It will result in the junction temperature operating below 175, and therefore it is continuous. So you can apply that, no problem. The challenge, however, and in real life application, the challenge is maintaining that 25 degrees on the mountain base, and therefore care must be taken to always monitor that temperature. And if it is very difficult to maintain it, and therefore the recommendation is to make sure that your application caters for the timing, for how much timing you're allowed for that current to be through your PCB. But in a nutshell, provided these two conditions, the T junction is below 175 and the mountain base is maintained 25 degrees, then that is continuous, and you can apply that on a DC basis.
Can I just add to that? Sammy mentions keeping the mountain base at 25 degrees C. If we look at the image of the demonstrator gear in front of us, you can see we have some cables. So you can see the red and black cables that we use to as part of that circuit, so that we get the current flowing via the MOSFET to those load wires. If we was to put a thermal camera onto that, we would find that the wiring in that circuit is hotter than the MOSFET. So the effect we would have is that as those black wires, which connect to the copper bus bar that the MOSFET's on, they start to heat up, which will heat up the copper plate, which would heat up the mounting base of the MOSFET as well. In a real application, we would usually find that it is the circuits or the PCB's inability to take away that heat, which would cause, more often than not, the mounting base of a MOSFET to rise. The MOSFET has got a very low RDS on, and we wouldn't expect that to be causing all of the temperature rise. We usually find that the circuit itself can cause the MOSFET to get hot.
Thank you, Stephen. The next question is, if the devices are high current and low RDS on, what is the impact on SOA linear mode?
I can start that off if you want, Sammy.
So you can, yeah.
We, for all of our lower voltage trench MOS products, our aim is to never sacrifice the SOA capability of a product in order to achieve the next gen. So what you would find is for a lot of our products, as we go to the lower RDS on, we do that without sacrificing the SOA, and the SOA usually increases. So for this product, it's our latest gen product. The SOA capability is about 40 amps, so it's about 38 amps for a 10 millisecond pulse for VDS of 10 volts. We compare that to the previous generation of a similar type, and that is about 4 to 5 amps better. So we don't sacrifice the SOA capability. In fact, there's a region of the SOA plot where that IDM limit is the peak current that you can ever achieve in linear mode. So for very low VDS voltages, so wired at the less than 1 volt, for example, the high current capability that 2000 amps capability would determine the SOA capability. For the rest of the SOA plot, this is more of a time power envelope. And again, we achieve a very good performance. We don't sacrifice any of that performance as we go to our next gen low RDS(on) high current products. Anything you can add to that, Sammy?
The only thing I would add is that sometimes there isn't an obvious link between RDS(on) high current capability to SOA. However, I do have to emphasize that the technology, the superjunction technology we adapt at Nexperia, has got the advantage of SOA performance. On the top of that, the devices that are destined for application where linear mode is of relevance, and they are optimized further, and they give the strongest SOA there is in the market. So it's the technology itself that is robust for SOA, and it's not necessarily just because the MOSFET is capable of high current or has a low RDS(on) will necessarily result in a good SOA performance. The technology itself and the optimization that we would take care of would give it this strong SOA performance.
Thank you both. Okay, you've already covered this in the PowerPoint, but it's worth asking again. Is the current rating calculated?
I'll leave that for you, Sammy.
Okay, it isn't in a short answer. I mean, there is an application note coming out that details actually everything to do with continuous current as AN 9016. I will still give you the answer now. The current rating that we state in the data sheet is verified through testing. And by that, I mean, we verify it through the time length that we are more than confident it achieves the DC rating. I mentioned more than 30 seconds, while the actual DC is within 1 second. On top of that is we cater for any parameters that provide the limiting factor. Now, the parameters that can provide or can be the limiting factor could be a test board, it could be the actual test gear, or anything that stops us from verifying the figures that we give in the data sheet will be the limiting factor. So the figure that we give in the data sheet would have gone through all these hurdles prior to being put in the data sheet. The actual capability or the theoretical capability is higher than that. And that's what we mean by this figure is not verified through design, as in theoretical, but it is actually verified through testing.
Super. Thank you very much, Sammy. Okay, that's all the time we've actually got for questions. We haven't got around to answering all the questions that have come in. So as before, we will collate those. We'll get the team to put some answers to those, and we'll publish them online after the event. Thank you to Stephen and Sammy. Thank you to everybody who contributed with questions as well. You can take a look below this video for more details of these products, including the product data sheets and also details of our NexpeRiA S3 family of MOSFETs. Stephen already mentioned, but you can actually view the high current MOSFETs in action on the on-demand section of the industrial channel. There's a good video over there, so go and take a look. If you've got time, stick around. We'll be back in about 5 minutes for the next live discussion on the thermal performance advantage of clip-on flat power package CFP60. See you soon.
Thank you.
Okay, thanks.